Okay, so in that first part of the lecture, what I've tried to do is introduce data structures as a motivation for the mixed models, and I now want to introduce the concept of a mixed model itself. Now recall from lecture 6.7 that we derived a generalized least squares estimator that can accommodate non-spherical errors, and we talked about heteroscedasticity and autocorrelation for models that had error variance equal to sigma squared times some positive definite matrix that we called omega. Now the key practical limitation of GLS is that we often don't know the exact form of omega, and instead we must derive some assumed parametric estimate which we plug into the FGLS model. And of course, since it's easy to misspecify that estimate, we said in section 6.8 of the lecture that if our interest is simply in obtaining good inference on beta, a preferred approach is possibly robust inference. But, and this is the key insight, and I've highlighted it here, in some instances, the general structure of omega is known, at least approximately, and it can be specified up to relatively few unknown parameters. And this is the principle underpinning and motivating mixed models. They are particularly suitable for clustered data structures in which there's a natural partitioning of observations into groups. The classic example of such structure is longitudinal data, of course, where we have observations on the same subject to be correlated, we assume are correlated because they come from the same subject. And that's the example data structure that we'll use to explain the concept of mixed models, and we'll begin with a simple motivating case. So the figure here plots data from a well-known longitudinal study on the heights and standardized ages of a sample of boys, 26 boys from Oxford, each measured on 9 occasions. So height is the response variable measured on the y-axis, and standardized age is the covariate measured on the x-axis. And just looking at the plot, just eyeballing the plot, you can see a pattern that's typical of longitudinal data. The growth patterns, or growth curves, show a similar pattern across subjects, a positive linear trend in this case. So height is going up as we would expect to happen, it's not decreasing. But we can also see important individual differences, both in the intercept values and in the slopes. Some slopes are flatter, some are steeper, some of the intercepts are higher, and so on. So the question is, how should we model the relationship between height and age? How do we go about modeling this data where there's clear dependency for each individual, but there's a broadly similar structure of pattern in growth over time, and that is to say, slopes that are increasing? So, there's three candidate models we could consider to model the longitudinal data, which look reasonable given the plot. The first is a population average model, shown here. All we've done here is we've pulled the data across all units, all boys, and we've estimated a single intercept and a single slope. Now these parameters measure the population average intercept and slope, so they tell us on average how the height of boys grows with age, but there are two drawbacks here. First, least squares estimation is going to assume constant error variance, sigma squared times the identity matrix, but there must be within subject correlation because the same units are measured repeatedly, and ignoring it is going to lead to biased estimates of the standard error, so the off-diagonal elements are not going to be zero, as is implied by the identity matrix. Second, we could estimate between subject differences in growth patterns, so we estimate a subject-specific model. We estimate the model for each unit, and that would give us 52 estimates, 26 times the intercept and times the slope parameters. But again, there's two drawbacks. First, population inferences would require us, if we want to find out about the population, that would require us to conduct a second stage analysis using the first stage subject-specific data, because we've estimated this at an individual rather than a population level. And that requirement for a second stage is inefficient and could propagate uncertainty. and so on. Second, these models, these individual models, are ignoring the common growth pattern that we observe across individuals. Again, we're failing to use the information in the data. By separately focusing each model on an individual, we're not generating inference collectively from across the population as a whole. And the within subject errors could also be serially correlated, which is another problem. Now, the third model we could estimate is the linear mixed model. And the way a linear mixed model works is it's going to pull the data across units and estimate the model shown here. So YIT is equal to beta naught plus beta naught I plus beta 1 plus beta 1I plus times x IT plus an error term. So notice that we've got a parameter here that's global and one that's relevant to individual I, and a parameter here that's global and one that's relative to individual I. And that's how the mixed model works. It strikes a balance between models 1 and 2, the population model and the individual model, by incorporating two distinct types of parameters, or what in this area of statistics is known as effects. First, we have the fixed effects, beta naught and beta 1. These are fixed values which capture the population average behaviour. Then we have random effects. We've not come across these before in our models, the statistical models we've looked at so far. These are random values drawn from a distribution, which allow for between subject variation. So they allow each subject that we're looking at to deviate from the population average captured by the fixed effects. So the major innovation of the linear mixed model then is the inclusion of these BIs as a vector of unknown random quantities, similar in character to an error term actually, but whose value can be specified up to a relatively small number of parameters. That's the point. The random effects are, before I go on to talk about the random effects, just something on notation for longitudinal data. So we have big N units, that's the number of units in our sample, I equals 1 to big N, each of which has Ni measures made over times t, so that gives us a total of N, small n, equals the sum over I to N, Ni sample observations. In matrix form, for unit I, the longitudinal model is written as follows, shown at the bottom. The response vector is equal to a design matrix times the fixed effects plus a design matrix times the random effects plus an error term. So in a mixed model we have two design matrices, one for the fixed effects and one for the random effects. Okay, let me just focus on the random effects because that's the new part, if you like, that we haven't seen before. Now the random effects in the mixed model are assumed independently distributed as multivariate normal with mean 0 and the covariance vector, covariance matrix, shown here. In our example, psi, the covariance matrix, contains three parameters: the variance of the intercept random effect, the variance of the slope random effect, and the covariance between them, shown here on this diagonal. The three unique variance parameters in the linear mixed model, the two random effects variances and the error variance, are referred to as the variance components. And here's the parsimony of the linear mixed model. Only 6 parameters need to be estimated: the two fixed effects, the within subject error variance, and the 3 parameters in psi, irrespective of the number of subjects that we observe. So if we had 26,000 subjects instead of 26, we would still only need these 6 parameters in order to be able to calculate both the fixed effects and the random effects in the model. So in that sense, a linear mixed model is truly scalable in the number of subjects, and that's one of its key advantages. Now, in addition to being parsimonious, the linear mixed model offers 2 further key advantages. First, in a single step, it provides information about population behaviour as well as between subject variation in behaviour. And secondly, it accommodates within subject error correlation and heteroscedasticity. So it accommodates non-spherical error scenarios. So what we'll do now is we've looked at this specific example using the Oxford data to motivate it. I've tried to show you how the model for the Oxford data would look in this simple setting of just one covariate. These are the random effects, the covariance matrix of the random effects. And we're now going to generalize the linear mix model to the multiple covariate setting, explain its components, and then look at how it can be estimated.